Yeah, so like we said, right, we're going to be talking about the future of quantum software development. Just to start things off, talk a little bit about Classiq and who we are. We're a 3-year-old startup at this point. We've have about $63 million in funding to date. We closed our Series B funding about mid last year. We have a pretty large team of about 70 plus world class experts, most of them software developers, and they're coming up with amazing things every week. Gosh, they move fast. And we have offices in Tel Aviv, Israel, in the US, where I'm based, in Europe, and we're going to be opening offices pretty soon in Japan too. And right, so I'm excited to see whoever wins the Quantum Computing Today challenge, and hope to see you in Israel when you win and head over. So I'm also excited to see what that prompt is for the Quantum Computing Today challenge, and that'll be fun to see tomorrow. We're partnered with quite a few of the players in the field, right? IBM, Microsoft, NVIDIA, Amazon, and largely, right, so, Q Control, Cold Quanta, and a bunch of universities and enterprise partners as well. A lot of them for integrations, but a lot of them also to connect and have a seamless integration with hardware. And we'll talk about that in a second. But as it pertains to kind of the challenge problem, what we're all here today for, as you're going to see right in your challenge prompt as you're going into it, we're starting to face kind of a quantum software challenge, right? It's fairly easy to go ahead and do a problem or solve an algorithm or build your circuit for about 5 qubits. Once you start getting to 10, 20 qubits, it gets complex and takes a hot minute, that's for sure. Right, to make sure you have all your C naught gates in the right places and things like that. You're uncomputing properly. But once you start getting to 100, 200, God forbid, 1,000 qubits, that's just going to be impossible to go ahead and design and move forward and debug, right? I'd miss a C naught gate somewhere in a 100 qubit circuit and it would just not run, right? And right now, there's not any intelligent ways to debug a quantum circuit and figure out where that issue is. But this isn't the first time an industry's faced a scaling problem. So about 60 years ago, this was happening in architecture, right? Architecture was done by hand. Your engineers are drawing out the diagrams brick by brick, right? Making sure that it meets structural integrity tests, right? That the angles are going to be right for it, that it's not going to collapse on itself. And the way that was solved was through automations. Right now we have Autodesk and automation tools that kind of abstract it out, make it easier for you to do very large projects. And making it possible to even design buildings that weren't possible before, right? So where you had to do it, by hand, now we have these automations that will do your structural integrity tests for you, figure out where the faults are, and help you correct where those faults might be, and maybe even give you a suggestion. Similar things have happened, in electronic chip design, and this is hitting a little bit closer to home. In the late 1960s, we're starting to get to 100 transistors on a chip, hundreds of gates on a chip, and they're starting to realize that it's not tenable to be doing this by hand anymore. And well, that sounds like a very familiar problem, doesn't it? And the way that was solved was through electronic chip design, right? We by defining what you want for the chip at this higher level functional way, now we have automation to take that functionality and design that chip, and now we can have chips with billions of transistors without kind of any headache whatsoever, right? Um, and that's what Classiq's doing for the quantum community. We have a quantum algorithm design platform, and our platform automates the designing of quantum circuits. We have abstraction, so you're not programming things at the quantum assembly language. It's highly scalable since we're defining things at this functional level as opposed to the assembly language. So it can scale to hundreds, thousands of qubits. We have clients today doing circuits for 1,000 plus quantum circuits that they can't run on actual any hardware right now, but they can compute it and have it out there for the next series of quantum computers that come out. And of course, highly usable and friendly to go ahead and manage and walk through. But talking about where we are today, right? As you're computing quantum circuits, you have to go through kind of a formulaic process where you first define what is that problem you want to solve. Then you go ahead and you figure out, are there any pre-existing schemes or algorithms I can use to solve that problem? Can I modify that for my specific use case? Can I optimize that circuit then? And then that last little bit is automated, right? The compilation transpilation as it hits the hardware bit of things right at the tail end. But that leaves a lot of the design space open, right? If you define things at the functional level, right? If you define things at this higher level mode, you can tap into much more of the possible design space, right? It's a huge phase space of qubit count, circuit connectivity, right? Depth of your circuit, and trading off one for another, or figuring out how do I optimize, or picking different implementations. That's a huge data set and a huge phase space to go ahead and navigate and try and figure out. When you define your circuit and you hand that to a transpiler, it can do some optimization right at very local area of phase space. Maybe move a gate around, do some quick gate cancellations. But for example, if you're looking at multi-controlled X gates, right, in that design space, there's a ton of different implementations that all do the same functional output. And it takes a lot to try and figure out, okay, which implementation do I need to use for my use case, for my hardware, for that hardware circuit connectivity? Is it possible to use this implementation or that one? How will that play with the number of qubits? Will it fit in there? Well, I want to make sure, maybe you're trying to crunch down the how many steps there are in that quantum circuit, so you don't have a noisy output at the end of the day. And there's all these considerations to play with and try and figure out and map out, so you have an optimal circuit that works for what you're trying to do. So while a lot of this is manual today, what we're doing at Classiq is automating much of that process. So we're saying that users using the Classiq platform, you define what you want your quantum circuit to do at this functional level, and the steps after that are automated by the system, right? And so you define your functional model, and everything after that is hardware constrained, right? The functional model is what you want that circuit at the end of the day to do, to implement. That's your novel algorithm. That's your design challenge, your problem, what that output is that you want it to compute at the end of the day. Everything else is implementation, right? How do I execute this for IBM's hardware? How do I execute this for this number of qubits, that gate set, the circuit connectivity mapping, the gate fidelity, right? All those are hardware constraints for the model that you're building, and it's just implementation. And that implementation is going to change, year by year as new computers come out, as the gate sets change, as the hardware changes, as fidelity gets better. But your model, the functional model, doesn't change, right? And that's why we're defining things at this higher level gate, higher level abstracted layer away from assembly language, so that you don't have to figure out, all the possible designs that you can have that all do the same thing, right? They all execute that functionality. Which one is the best for your specific constraints, for that hardware, with that gate connectivity, with that circuit, fidelity, right? And at the end of the day, the Classiq platform ends up being kind of a one-stop shop for you navigating this space. You define things at this higher level modeling away from the assembly language. The circuit will be automatically synthesized using the Classiq platform. And we also have analysis and execution all within the platform as well. So we're trying to make it easy to define what you need and want to do, have it be automatically synthesized, no matter how many qubits it might require or the depth it might require. And then you can go ahead and do things like debugging and execute your circuit. And we're partnered with all the hardware modalities, right? We're partnered with all the quantum cloud-based hardware vendors, the quantum cloud vendors themselves, AWS and Microsoft Azure, quantum simulators like NVIDIA, IBM's, and Intel's, so that you can go through the entire process within the platform and kind of keep it nice and tidy. We don't have to make this entirely academic. I can show you a little bit of the software here. Here we have a video showing our integrated development environment. It's web-based, so you can go ahead online and use the software. On the left side is that higher level functional model. We have a couple of state preparations going into an adder. And on the right side are all the constraints, right? We keep them separated. You have your model, and then you have what are those system constraints you want. We're saying give us a circuit with a max width of 11, max depth of 250. You can add other constraints like the hardware you want to run on, so you know what that gate connectivity is and that gate set. But here we're just going to say go ahead and synthesize that. So that gets sent to our server, and it's essentially a giant constraint satisfaction problem, and it gives you a quantum circuit that meets your constraints. Here we have a circuit depth of 90. It gave us a circuit there, and you can expand out any of these kind of higher level blocks, right? We have two-state preparations going into an adder, and you can see how did the system implement that adder? How did the system implement those state preparations? And you can even click on one of these blocks and see further detail on that implementation, right? What do the registers look like? Um, and then once you're done analyzing and taking a look at that, you can go ahead and execute on any of the hardware vendors, any of the simulators that are available. And simply right here, we're executing on IBM's AER simulator just for brevity, so we don't have to wait in the queue. And you have your results out. But as it pertains to hackathons or academia or challenges in general, what Classiq's recently done, we just launched our academic program. So we have our platform free and available for students and professors. And along with this, Microsoft's our launch partner for it. So there's free Microsoft Azure Quantum credits along with this. So if you're a student or a professor, right, if you have an @edu email address, I highly recommend you go and visit classiq.io/academia and register for free access to the software. So we're going to start releasing the software in waves starting the first of this coming month. You can have access to it, right? Use it for free and use, real quantum hardware and quantum hardware of a measurable size, right? You can play with quantum computers that are more than just 5 qubits and actually see what your quantum programs look like in real life. So here's a QR code for anybody who would like to go ahead and scan that and get access to that immediately, or you can go to the URL that'll be shared as part of this as well. I'll be on the Discord channel after this call too. So if anybody has questions about the platform, if anybody wants to discuss this a little further, or even talk shop about the Quantum Computing Today challenge that we're sponsoring, feel free to let us know. Feel free to have a chat with me. And right, I always like to show the software running live, right? It's always fun to have videos of it and things like this, but I'm actually going to dip into the software and show you what the software looks like running it in real time. So we have the integrated development environment we showed you in this quick video, but we also have a Python software development kit. So if you want to, add some extra graphics packages or have a little bit more fine-tuned control, we also have the Python SDK that you can play around with. And I'm actually just going to dip into a Python notebook I set up for this. Here's our QHack workshop for the Classiq platform. And let's just go through it live and see what it looks like to actually use the platform and solve some problems, right? So here's all our, loading our libraries, import Classiq. Just going to load that up. Log into Classiq. I'm already authenticated, so I'm not going to do that again. It'll give me an authentication error and say that I'm already authenticated. And one thing I definitely wanted to show you as part of this is kind of the power of the system, right? The benefit of defining things at this functional level. Here we have a very simple circuit, right? We're just calling out an adder circuit with 2 quantum registers of size 2. And we're telling the system that we want this synthesized for IBM's hardware, in this case, IBM Quantum's Tokyo, and optimize it for the circuit depth. And at the end of this, we're just calling out synthesize this adder for us with those parameters. So we're going to go ahead and do that. It's getting sent up to our servers. It's getting analyzed. It's going to be sent back. And perfect, that executed correctly. And now we're going to go ahead and say, show us that interactive circuit. So I'm going to click that. And when you click the show interactive, it actually does go into our integrated development environment, right? You can go ahead and see the synthesis and then execute this if you want us to as well, all within the platform. And you can expand it out and see what is that adder? How is that adder implemented? And in this case, the system thought it best to implement a ripple carry adder for this hardware. Let's go and let's see. Below this, we have the circuit connectivity map for the circuit we just generated. So you can see how does your circuit play, which qubits talk to which qubits in your circuit. And you can even see how does this map out to IBM's Quantum Tokyo that we wanted to run it on. Which qubits is it going to be using? Okay, so here's the qubits going to be using, the 6-qubit quantum circuit. And then you can do some fun analysis of your circuit as well, right? Plot the heat map, see the gate histogram. And, the heat map looks much more impressive when you have about 1,000 qubits. But it's still good to know which of your qubits are being used more or less, right? You certainly want, the better fidelity qubits being used more often than not. You can see, how many single versus multiple qubit gates you have. So do some of that analysis. But we also want to show that you can go ahead and see what would your code look like transpiled onto actual hardware, right? If you're going to run this on various hardware, what is this going to look like? And we're just showing a quick example of comparing Microsoft Azure's quantum hardware versus IBM quantum. And you can see what would that circuit be on those hardwares transpiled. So, here's the depth, multi-qubit gate, and total gate count running on that hardware for your circuit. And instead of filtering by device, I'm going to go ahead and filter by depth. And you can see that the computer that the circuit is most optimized for, uh, ends up being, to no one's surprise, IBM Quantum's Tokyo, because we optimized for it. And if you tried to run it on any other hardware, it's unoptimized for it, right? That shows some of the benefit of specifically building your quantum circuit with specific hardware in mind. That's terribly important if you want to build large scale quantum problems that might not be able to be run today, right? You might think that it requires 200 qubits, 100 qubits or so, and it might not fit within the hardware you're looking at. But by properly optimizing your circuit, you might be able to get to a constraint or an implementation or a size that it is quite possible to go ahead and execute the kinds of circuits that you're looking for today. Um, so here we optimize for IBM Quantum's Tokyo. Here's a depth of 27. And what if we said, you know what? I see that Azure Quantum IonQ's the second on this list. What if we optimize for that hardware instead? And here, right, I'm just going to go ahead and click run on this. We're not changing the function, right? It's still an adder. We didn't change it. We didn't call out anything else. Our algorithm is the same algorithm. We're just defining different constraints for that algorithm. You don't have to touch it again, and you can just play with different constraints and see how that gets executed differently. And in this case, for IonQ, it's saying that a quantum Fourier transform adder is the better implementation in this case. So we can go back and see this. So I went ahead and ran the qubit connectivity map. Much more interconnected in this case, right? Kind of a star-shaped pattern. And I'm going to go ahead and see what would this look like on the hardware itself. And cool, right? We can see that IonQ's hardware is much more interconnected than the IBM's Tokyo, and that's because it's this trapped ion technology that is all highly interconnected, and so it allows for some more complex algorithms with more qubit connectivity than you would on a more kind of dispersed map. So there's different implementations that are more feasible on this hardware because of the circuit connectivity. And thankfully, me as a user who's just kind of going ahead and I know I want to do an adder, didn't have to have all that foundational knowledge of what is the circuit connectivity, how do they connect, what's the gate fidelity. The system understood that and it went ahead and implemented the best implementation for that case. And we can go ahead and do some analysis on this too. We can see the heat map and the gate histogram, and how this maps out to the various hardwares that's getting transpiled out now. Perfect. And you can go ahead and let's again filter by depth. And sure enough, the hardware that this is most optimized for is Azure Quantum's IonQ with a circuit depth of 12. So actually much shallower, right? Same implementation, much shallower. And again, it's the most optimized for this hardware because we told it to be optimized for the hardware. So you can do some pretty fun things with optimization, and that's the importance too of defining things at the functional level. Instead of giving the system a quantum Fourier transform adder and telling the transpiler to go ahead and optimize, if you gave a QFT adder to IBM's Tokyo, it's going to get transpiled to something that's not going to be very efficient because the circuit connectivity map doesn't make sense for that. So by defining things at the functional level, it allows the automation to find the best way to implement it, not just kind of moving a gate or two around. There is a huge design space that can be analyzed and is analyzed by the system when you go ahead and put in that model of what you want to do. So looking like we have a little bit of extra time, I can go into this little bit of an extra example, slightly more complex circuit just for fun. I was actually playing around with this a little earlier. It's a Grover's algorithm for a Secret Santa. And this one's just fun. If you ever want to do a Secret Santa in the future, Christmas comes around this year, run it on a quantum computer, right? You can have some fun, and that's always a nerdy fun thing to talk about. So, here we have, Allie, Berta, and Charlie, and, the same one person can't get more than one gift, things like this. So just quickly implementing this, we called out each of the possibles. X1 to X6. We said that they have an input register size of one. And the formula for the Grover's algorithm is X1 but not X2, X3 but not X4, things like this. And all I said is, here is my formula. I want it to be implemented in a Grover operator and then execute it for me. Just give me a single solution out of this so I can see, what is my secret Santa, at least what's a solution to the secret Santa for me so I can go ahead and know who's getting what gifts. Again, right, it goes into the integrated development environment. You can see the code and play around with it, but for quickness, here's our Oracle, our mixer. You can deep dive into the Oracle and see all this fun stuff. What is a bitwise or statement and how that got implemented. But if we go back, here's our secret Santa, right? We got X1, X4, and X5. And you can see, okay, here are the people who are getting these gifts. Allie and Berta, Berta and Charlie, and Charlie and Allie. So definitely going to be a fun and fun one if you ever want to do in the future and have some fun doing secret Santas. But essentially, that's the power of the platform. And if you're interested in it, please do go ahead and sign up through the Classiq academic program, right? So classiq.io/academia. You can go to this webpage and click register and have fun with the platform. All
Thank
right.
you. Thank you so much for your presentation, Eric.
Mhm.
I definitely love how your people are not called Alice and Bob, but Ali and Berta. um,
Yes.
and yeah, the live demo is always very useful to understand exactly what you meant. Like the presentation was very good, but a live demo also adds an extra very cool layer. We
Hmm.
have a couple of questions, but we're only going to have time for one. So we're going to go with a question from Dentucky Kirby. Do you think that quantum computers should be gate based? Are we looking at programming large scale quantum computers the wrong way?
I definitely believe in the modality of gate-based quantum computers, right? There's certainly applications for quantum annealing that certain problems can be solved more efficiently through a quantum annealing computer, but gate-based quantum computers allow for a larger scope of problems to be solved. And so, if we're going to be focusing on a modality of quantum computers, certainly from my standpoint, I believe that gate based quantum computers is the way to go because it's going to benefit more industries by developing that technology.
Okay. And then by using Classiq, then you can optimize it.
Exactly, right? We're trying to make it easier to integrate with these very cool quantum systems and hardware so you can take advantage of all the really cool and interesting things that are happening.
Okay. Thank you so much, Eric. Thank you for everybody asking your questions in the chat. Make sure to go to Discord to ask more questions to Eric.
It was a
Thank you
pleasure.
so much.